if more people show up, they should be able to just be able to log in through the with the Zoom ID and the Zoom password. So I'm David Newsom, the president of HAL5, and I would like to welcome everyone to our first webinar event. And we'll be doing the webinars for the foreseeable future as we have the COVID-19 quarantine going on and the library in downtown Huntsville is closed. And as just to do some announcements, I'm going to share my screen here. Wait, it should be, let's see. I'm going to first share the announcement. You should now be able to see a PDF flyer for Jim Plasko, who's the president of the Chicago Society for Space Studies. He'll be giving another HAL5 webinar on Thursday, July 9th at 7 to 8:30 p.m. Central Time, again through a Zoominar, which we have, and I'll be sending out a flyer. For those who are not members in HAL5, if you want, feel free to send a chat, or you can contact me to get a flyer copy. I'll actually, let's see here. I'm going to put my email address. This is my Yahoo account. So feel free to contact me if you have any questions about the July talk, again on July 9th. And let me we'll do one more thing here. So for the July 9th talk, it'll be on the planet Earth as art, the view from space, and Jim Plasko will give a discussion of how you can view the views of our planet as a artistic, as a type of art. And that should be a pretty neat talk. And I can send a flyer, just contact me. Other things to announce will be let me just bring this up here. Let's see, here we go. We also have a event. This came out today. I just found out about this today. Our Vice President David Hewitt brought this to my attention. There is a microbiome for Mars virtual workshop, which we're trying to spread the word for this. And this workshop will be, I'm going to send a link to the attendees inside a moment, but this will be a workshop you can attend talking about, it's going to be hosted by Trish, the Translational Research Institute for Space Health, and they'll be discussing the type of micro level life forms inside Mars. So this should be a neat talk as well. I'm going to send that link over the membership now. And then one more thing will be, let's see here, I'm going to bring one more thing here, so I'm going to share my screen here real fast for one more thing. There's also a solicitation for a proposal it's a deadline of June 26th. This is also sponsored by Trish, and this is talking about how to protect astronauts, to predict, prevent, diagnose, and treat adverse changes for people involved inside space travel. And I'm going to send that link out to the membership right now. So those are a couple events and talks coming up in the near future. And so with that, I'd like to introduce our first webinar speaker, Dr. Peter Swan, who is the president of the International Space Elevator Consortium. And with that, I'd like to hand over the forum to Dr. Peter Swan, who can give a more detailed bio sketch of himself and some of his background.
Well, good evening, everyone. Well, I'd like to welcome you to an evening where we should be thinking big. We're not only talking about a mega project here, space elevators, but we're looking into the future. And we want to dream also of what has been in the past. So I need each of you to think big. We're going to open up the solar system through this whole arena, and we're going to really assist the migration towards colonies out there in space. In reality, the space elevator complements and is compatible with a rocket architecture. And that'll lead to space access that is routine, daily, safe, environmentally friendly, and inexpensive. What we're going to do is we're going to dream what can be. And most importantly, each of you can be a part of that. But first, thanks to the Huntsville L5 Society, the National Space Society chapter. And I want to thank David for leading the way and helping us execute this. But what we want to do is we want to focus on the designs and concepts of Professor O'Neill. He visualized 10,000 people in a colony of rotating torus in space when other people were just barely getting over the fact we could go to the moon. For you that don't know me, I'm Pete Swan. I've been there and done it. I love having white hair. You know, you can be a professor and everybody thinks you've been there, done that. 50 plus years in space systems. Started in the Army, a little bit of West Point time, then did some Army Science Board stuff toward the end of my career. I then did 20 years in the Air Force, space stuff, of course, and did a few years on the Air Force Scientific Advisory Board. Oh, by the way, I also did NASA. I was at JPL for 2 years. Oh, and then I did commercial space. I did 10 years of building the Iridium system, the first real production commercial satellite constellation. Oh, and then I was also in academia. I did a little PhD along the way. I taught at the Air Force Academy. And then after I retired out of Motorola and the Air Force and everything else, I did 20 years of teaching industry and government how you do space systems. My passion has always been starting with mega projects. What are they? How do they work? And how do you figure out what you have to do and what you have to build? Today, we're going to disrupt your accepted approach to developing the O'Neill spinning torus colony at L5. How do we do that? Well, along the way, I'm going to show that the space elevator is closer than you think. We're going to talk about space elevators being compatible and complementary to rockets. We're going to talk about research that's in the labs that's proven that we have a tether material that will work for space elevators, long enough and strong enough. Research at Arizona State University has shown that we can get to Mars in 61 days. Now, wait a minute, put that in your pipe and smoke it. 61 days to Mars. Now, that's not every trip. We can depart for Mars every day from space elevators. Oh, wait a minute. We don't have to wait 26 months for a launch window. Oh, remarkable. So we can leave every day. Now, the trips aren't all 61 days. There's some of them that are 400 days. Some of them are long. But we can depart every day for Mars. In addition, we can move massive amounts of cargo. Think about 178,000 metric tons per year to GEO and beyond. Okay, I've been aware of space elevators for 37 years, been working with them 18 years, been in the International Space Elevator Consortium from the beginning, and all that kind of stuff. Now I'm going to dump my video here. We don't need that. Let's see, video, stop video. There we go. That should stop it. Then I'm going to call up the charts, and we should get going here. Sure. Then we hit this, and then we can get going. Okay, what we're going to talk about today is the connection with the L5 concept to the space elevator. So you can see that I've drawn the diagram of the L5, and it basically is the same as going to the moon. So I got two questions for you to think about over the next hour. How bad is the rocket equation? Okay, you know the answer to that is poopy. We only have rockets today, so rockets are what we need, but maybe we should think bigger than that. Why go to the moon to build an L5 society? If you look at all the documents, they have us going to the moon, setting up a colony on the moon, manufacturing stuff on the moon, and then sending it to L5. So we can't build L5 until we set up a colony at the moon. Wait a minute, is that the right answer? Why don't we just go direct? Okay. So what are we really talking about? We're talking about space elevators and where we're going. What do the customers need? That's what I think about in demand pull. We're going to talk about where the space elevator is today. We're going to talk about international interplanetary support that Arizona State University kind of developed a really neat space research project on. And we'll go from there. Whoa, wait a minute. I just lost my charts here. Now I don't know how to get them back. Let's try that. Okay. Oop, let's see. Boy, this is bad juju. Okay, you guys can all see the charts, I hope. There we go. I got it. Okay, they're back. Okay, we're back. My conclusions is that if you really, let's see, did I skip a chart here or something? Let me see what, yeah, I skipped the chart too. Let me go back to the beginning here. Oh, what the heck? Okay, there's a look at, I'm going to get there. Excuse me, I'm sorry I made this mistake here. Okay, let's start here. 2019, a big year for space elevators. We transitioned from a simple concept of a space elevator to an enterprise-based Galactic Harbour. We'll describe a Galactic Harbour in a little bit, but it's basically 2 space elevators. Then we've got a material and we've assessed the preliminary TRL levels of every segment of a space elevator, and they all come out at 3 and above, except for the material, which is in the laboratory. We've got to move it out of it. But we're working on that. So the material for this space elevator tether is there. The concept, this is a big picture for you so you can get ready for the discussions on L5. 3 Galactic Harbours, which are 2 space elevators apiece, 100,000 kilometers long. And you do that, you can get to mature space elevators and provide 170,000 metric tons to GEO and beyond. It really is where the transportation story of the 21st century meets the final frontier. Space settlements design, L5. You could go to the web and find 47 different documents on the L5 Society. There was a lot of work done in the 60s and 70s and 80s on the L5 colony. The bottom line is they need 11 million metric tons at L5. Now, the concept in the old days was to go to the moon, mine the moon, create shielding, create solar panels, create windows and all that kind of stuff, and then use electromagnetic mass launcher to get it to L2. I mean, to L5. But the real kicker is that you have to put a colony on the moon before you go to L5. Space elevators can provide direct access to L5 with finished product created on the Earth. Now, let's think about that again. You create everything on the Earth where we have manufacturing expertise and capabilities. Then you ship it to L5, you skip the moon. How do you do that? You got to beat the rocket equation. So we'll talk about that in a few minutes. But this is what we're looking at. Space elevators out there, 100,000 kilometers. By the way, this isn't the scale, of course. You leave the space elevator at 7.76 kilometers per second when you climb up to the top. You can get to L5 in 10 hours. Now you're going fast, so you got to use rockets to slow down and rendezvous with the spot there. But the point is, you can move mass directly to L5. So the vision is to colonize space. That's been the goal since Gerald K. O'Neill wrote his book. NSS bought into that. Even today's mission says we're going to expand civilization beyond Earth. That does include colonies on the moon, Mars, and L5. But a new paradigm has come along. The paradigm is we can accomplish a space elevator. A space elevator can get you fast there, 61 days to Mars, 10 hours to L5. You can release toward Mars every day, and you can move massive amounts of stuff. Well, in addition, space elevators are Earth friendly. One of the basic things about space elevators is we can build space solar power satellites in the near future. And we can move all the mass up to GEO. We're going to show numbers in a little bit. no rocket exhaust, and no additional space debris in LEO. So then we have an offer to the future scientists of the world. We can provide to you any mass, any science experiment to any location in the solar system. Now, let me say that again. Any size spacecraft, any location in the solar system. All we do is climb up to the end of the space elevator. You've got automatic velocity. You release at the right time, and you go to where you want to go. Compare that to the weight limits today on any space vehicle, much less scientific equipment. Okay, rocket equations. That is a bummer, man. The basic of a rocket equation is you throw out little things real fast to the rear and you go forward the forward way. That's all it is. You're consuming your energy on the rocket and throwing away parts so that you can accelerate and go. Well, in LEO, to get to LEO, you can barely get 4% of the mass on the pad. To GEO, only 2%. And that's also translunar. It's also trans L5. So an example, Saturn put on the surface of the moon 0.5% of the mass on the pad because it consumed everything else. Oh, by the way, everybody keeps talking about how great Elon Musk and Jeff Bezos are. They're going to really beat the problem because they're going to be reusability and lower the cost tremendously. That's really good, but you still don't beat the rocket equation. The rocket equation eats you up. So how is this possible? It's simple. A working space elevator ignores the rocket equation, uses the electricity to get to 100,000 kilometers. When you get up there, the rotating tether, rotating with the Earth, obviously, it's like a rock on the top of like on the top of your head when you're spinning around your head with a string. The rock keeps it taut. Then you release the rock, and it's going at 7.76 kilometers per second. Daily, routinely, safely, robustly, environmentally friendly. A remarkable capability. So the conclusion that I have for the L5 Society is we need a permanent infrastructure for access to space with the characteristics of space elevators. Daily, reliable, inexpensive, massive movements, fast transit, all those things say I could build an L5 society with space elevators. So where are we going? Now we're going to talk about a few missions that are really critical to the future and how we do that. Well, we know what's going on today. The US is going to the moon. ESA is going to join us. China is going to the moon. Russia's announced they're going to the moon. Everybody's going to the moon. But the phenomenon that's occurring today is we're going commercially. We just had a contract awarded to 3 companies to build the vehicle that's going to land people on the surface of the moon commercially. So it's remarkable. We have a whole effort going on commercial space, new space, they're calling it. So the breakout year for 2020 is we're indeed going to the moon, whether it's 2024, 2028, whatever you want, someday like that. And NASA, the Congress, US Congress has said we're going to Mars after that. Then, of course, we have Blue Origin and Virgin Galactic going to space with humans. With resources and everything. We've got SpaceX and Boeing going to the ISX. SpaceX just went there with 2 people. Commercial contracts for delivery to the moon and the lunar surface. We're going big time. So the real kicker is we have to envision a new architecture, one where rockets take care of people through radiation belts fast. Rockets do low Earth orbit and mid-Earth orbits. But space elevators move the mass to the colonies and to the activities beyond GEO. So they really are 100% of the mass that's at the Earth port gets to the apex anchor, and then you release it there. So we don't have consumption of our rocket as we go forward. Growth of diversity mission or delivery missions. Well, the traditional geosynchronous mission that everybody knows about. We've put a few little other missions that we see developing at geosynchronous there. And then, of course, there's lunar and interplanetary. I guess it's a good point to say that I have a lot of information on my charts, and I'll make sure that David has a copy of my charts, PDF, so he can make sure you guys get them. So don't worry about reading them today. Just look them over and get a feel for it. Here's a chart from 2014 that defines a quantity of mass needed to support those missions. Now that's per year, 100,000 metric tons per year. So that's just an estimate. We can argue all day long about how good it is or whatever you want, but I've identified 3 reference missions that kind of put it in perspective. We have to have a geobase idea. Well, space solar power is extremely powerful. It turns out that the estimate is if we can put space solar power up, we can eliminate hundreds of coal plants. A remarkable capability. John Mankins is running this. He's an old NASA guy, and he's got lots of contacts around the world. Space solar power is going forward, but they still can't execute without a way to get to geosynchronous inexpensively. The rocket equation eats up the plan. Then there's the moon base. A lot of people are thinking about going to the moon and set up a base there. Mars colony. Elon Musk is really, really committed to that. And then, of course, the first of all was the L5 colony by Gerald K. O'Neill. 10,000 people rotating torus in space. Okay, the space solar power, a remarkable capability when we get it. We'll eliminate hundreds, maybe even 1,000 coal-burning plants by providing 12% of the 2060 Earth population with electricity for almost no cost. It's a remarkable capability. Now, don't worry about these numbers. You can argue all you want on these numbers, but if you say those are the amount of metric tons needed, and that number comes from John Mankins, then you have to divide by the number of metric tons you can put in a rocket, and then you can multiply. That's outrageous. Oh, and then look at the cost. Now, I said cost at $1,000 a kilogram. We're not close to that yet. But if Jeff Bezos and Elon Musk get it down to $1,000 a kilogram, it still eats you up. So the conclusion is that you must have a transportation system that is very economical. So we got to work on that. The next one is the Mars colony. Now, I took this information from SpaceX's website, and he stated that he needs 1 million metric tons to Mars to support his colony. Now, he said that on the Sunday morning CBS show. So I quoted him directly, 1 million metric tons. Okay, let's translate this to cost and number of starships required and the number of years. Oh, bummer. That's kind of a long time. Okay, let's look at the moon village. I estimated 500,000 metric tons to support the moon village. So you do those numbers there. Oh, it's still outrageous. Okay, now let's go to the L5 colony. As I said, there are multiple documents you can go through there. I estimated 11 million metric tons needed at L5, and they said they want 10 million from the moon. Wait a minute, 10 million metric tons from the moon. No. What we propose is we send all 11 million metric tons to the L5 from the Earth after you've actually developed the parts you need. It's a completed product that you deliver to L5, and all you have to do is assemble it at L5. So if you divide the number of the demand pull mass at your location by the capabilities of a galactic harbor, then early on, it might take us 80 years to do the fulfillment. But as we mature our space elevator, which is like a 10-year process in our game plans, we could supply your total amount of mass to L5 in 7 years. It takes you that long to build it. I mean, it's just, 7 years is a very reasonable number. Okay, everybody knows what the benefits of space are, especially from Space City, Rocket City. And we've all seen this chart. We're going there, no problem. But there's a new concept. We're not going with rockets that are going to be eaten up by the rocket equation. We want to send the mass, the cargo, the equipment on space elevators. We want to get there in 61 days, or at least low numbers. And we want to go every day, not wait 26 months, and we got massive support. So the new concept says, where is the space elevator today? How come I don't have it? It should be there today. I'm ready to use it. Okay, so now we have to think about where we are with the space elevator. The first is we've translated from having a single space elevator to an architecture with pairs of space elevators. The Galactic Harbour is a pair of space elevators that supports commercial ventures and enterprises along its whole thing. You can imagine a Marriott hotel at the Earthport, at the floating Earthport, or a Marriott hotel at GEO, or even at Apex Anchor. And somebody has to provide the McDonald's hamburger. So we're going to have businesses along the way. We have the material. We have done a very, very good job at looking at all the technologies required for a space elevator. And we've come to the conclusion they're all feasible. The International Academy of Astronautics, an organization with 1,000 global space experts, have done 2 studies on the space elevator. And the second one assessed the technology and said, we're ready to proceed. Case for space elevators, we're ready to proceed. We can do it. And the interplanetary mission support research that we just did tends to say that we need the space elevator if we're really going to reach beyond the low Earth orbit or GEO orbit. I've talked about these strengths before. I put them here so that you could look at them when you download the whole thing. But here's a nice little picture. Everybody knows it takes about 9.3 kilometers per second to get from the surface of the Earth to 17,000 miles an hour. Bummer, man. That's a lot of energy. Oh, by the way, that's 96% of the mass that was on the pad. Bummer. Now, if you want to go anyplace else, you got to add more velocity, like going to the moon. It's like 3.8 or something like that. It's a bummer. Well, wait a minute. If you have a space elevator that's 100,000 kilometers long, then you climb up that using electricity. Takes about a week to get to GEO, another week to get to the Apex Anchor. You'll be going 7.76 kilometers per second and no stinking fuel required. So there's a little difference in engineering approach. Here's a look at a Galactic Harbour, how you can release all the way along for satellites to go wherever you want. Here's what a floating Galactic Harbour would look like. You'd have a 2 tethered terminus, and then you'd have a command and control floating operations center that takes the logistics, incoming payloads, outgoing payloads, McDonald's food supplies, et cetera, et cetera. Then we've got the GEO region where we would be coming through the GEO region. And of course, each one of the tethered climbers could drop off something at GEO. Obviously, that's what we want to do for the space solar power activities. But then we can completely keep going and go up to the Apex Anchor. 100,000 kilometers up is where the end of it is. And you just release it from there. And you can go to Mars, just coast along, no fuel required, except for changing of planes from the equatorial plane to the ecliptic plane of the solar system. But, you know, that's where we need rockets. We love rockets, by the way. They are space elevators compatible, complementary, and we love rockets. We just don't want to get out of the gravity well that way. Okay, a recent webinar was given. And it was done by Adrian Nixon. So I stole a few of his charts. I'm going to go through them fast. But since the tether is extremely important, and everybody's been laughing at us for the last 20 years on the tether, I'd like to make sure that you understand we have a material today. In the upper right-hand side of this chart is a thing called graphene. 2 gentlemen just won the Nobel Prize 2 or 3 years ago in the discovery of graphene, which is only shortly, not too long ago. It's 1 atom thick, and they have grown a single sheet 1/2 meter long by 1/10 of a meter wide, that is a single molecule. Okay, 1 atom thick, single molecule, half meter long, extremely strong. And they've learned how to grow it. So once you figure out how to grow it and put it on a reel, then you can take advantage of the strengths. This chart kind of compares tensile strength with the density of the material. So you can see all the normal stuff, and then you can see the newest stuff over the last 20 years. But now we have graphene right there. 100 gigapascals, no sweat. Okay, so the graphene can be used. And now here's some other things about graphene that are just remarkable. The reason I show this chart is single crystal graphene is going to be developed by a very hungry commercial world for a remarkable material. And we'll just use it inside the space elevator community. But that's where we're at. Oh, by the way, just weeks ago, LG Technology figured out how to have a production of graphene, and their current first run was 1 meter per minute. I mean, 100 meters per minute. Let's see, 60, whatever it was. It was a lot. 100, yeah, it was a lot. It was fast. I think it is 1 meter per second. So now, if you're going to roll it all up and make it into a space elevator tether, it would be something like this, and that's what it would weigh. So getting it to geosynchronous by a rocket would be just a piece of cake. Then you pull a few of those together, you put them together, you run it down, and you have a tether. So the question is the tether made from single crystal graphene feasible? Yes. This comes from the research center at the University of Manchester in England, where they actually have this material under development. Engineering development. If you remember, I said we're ready to start the engineering validation, the testing. That's where we're at. I just like to show this chart to show that we're at the beginning, but we're certainly not at the beginning. So the IAA study I mentioned before says we've got all the different components ready to go into testing, validation testing, and that's true. All we need is a big contract to let somebody look at all those components and test them. Here's some studies just to give you a background. In addition to assessing the technologies, we've also looked at the tough problems. We have 2 studies already done on space elevator and space debris. Both of them come out and say the space debris is not a showstopper. We know how to deal with it. There are 2 studies you can go check on our website and read that. Okay, interplanetary support. Here's what was done at the Arizona State University research over the last 2 years with about 15 students. I'm not going to mention the strengths again, but they're there for you to use. The ASU research came up with 3 major facts. One is 61 days is the fastest we can get there with a 100,000 kilometer space elevator. Now, we can also move a lot of mass, and we have daily departures. They calculated all the departures from a rotating tether. The traditional approach is the Hohmann transfer. Why do we do the Hohmann transfer, which is depart on a perigee, go up to apogee? Because that's minimum energy required to get to Mars. So therefore, we use the biggest rockets we can get and put as small a material as payloads on it that we can, and that's the way we get to Mars. We don't want to do that. We want to use a space elevator that's long. The first number on the left there is the apex anchor speed. That would be 7.76 kilometers per second. If you grow the optional apex anchor to 150,000 kilometers, you're going 11.4. If you go to 163,000 kilometer altitude and release from that, your payload has solar system escape velocity. So I can go any place in the solar system. Okay, the key here to understand, it's not a complex issue. Instead of departing horizontally with the Earth, so you just put energy into the energy you already have from the rotation of the Earth, or the Earth's velocity around the sun, you add velocity to that, and that gives you the Hohmann transfer. We want to depart at an angle. So what we're doing is we're doing vector sums here, vector sum, and it looks like this. We're entering the ellipse at the side, not at the perigee. We're cutting the corner and going from the Earth's orbit to Mars' orbit, not perigee to apogee, but across an ellipse. That's the way we do it in 61 days. But of course, that's only in one optimum time in the 26-month planetary dance around the sun. And there's only a few of those 61 days, but then there are all kinds of other options. The kicker here is we're not depending on departing the Earth in this parallel activity and only doing a Hohmann transfer for minimum energy. We're ensuring that we have a lot of energy. So we can do this transition from the Earth to Mars in this silly 26-month dance of the planets. We don't have to wait. We can launch every day. Here's just an example they ran at ASU. This is minimum energy in the sense of what you have to bring along with you, what type of rocket you have to have. Turns out at this particular point, our equatorial plane and the sun's ecliptic plane are aligned, and so we just truck out there to Mars. We don't have to do too many little corrections along the way. Now the kicker here is, when you get to Mars in 77 days, you're really hauling tail. So we need rockets. There's no doubt about it. We need rockets to slow down and rendezvous with Mars or wherever we're going. Like if we go to HAL5, we got to slow down. Here's a concept that's hard to understand if you've just been a rocket guy. We want to send a diamond ring to my girlfriend in Mars. And so I look at the bus schedule and say, when's a good day to send it for 61 days? Oh, there's one. I'll send it then. Oh, but if I have a hammer I want to send, it's really heavy and it'd be expensive. So no, I'm going to just send the hammer on the low cost runs. Oh, they're 400 days long. So a bus schedule. A bummer, man. I've got a choice every day from 6 different space elevators rotating around the Earth to depart to Mars. I got all kinds of choices. I don't have to wait 26 months. Now, this chart I put in there because it's always fun to compare rockets to space elevators, but I'm not going to really talk about it. It's just hard to do massive movement of stuff when you have the rocket equation in effect. So what we claim is we can move massive amounts of cargo each year to our destinations. So basically the conclusions are that we have this new idea of a galactic harbor, which is an enterprise region where we have 2 space elevator transportation infrastructures. It's a permanent infrastructure. You treat it like a train. In fact, the Japanese actually call space elevators trains. In their terminology, they're really dealing with trains. So our strategy is to link space elevators and rockets and have complementary systems that are compatible. And then we use the proper approach to send the proper thing. We really need to get through the radiation belts fast, so rockets are perfect for people. And then, of course, pick a mission and pick a space elevator. And you can call it a government one, a research one, a logistics one, or whatever. You've got all kinds of choices. Here's the bottom line. If you need to move stuff to support your interplanetary movement, rockets are probably not the right answer. You need space elevators. And once we mature space elevators into galactic harbors that have full capability, we're talking about moving Elon Musk 5 million metric tons out there to Mars very quickly. And like in 6 years. We could do L5 colonies in 7 years. So we can literally support the dreams that have been there for years. Gerald K. O'Neill could not do his mission. We can show that space elevators can execute it. Here's the vision. 6 space elevators in 3 galactic harbors, each tossing out a capability of 14 metric tons per day. Now that's the beginning. It's 79 metric tons when we're mature. And you can see how the capability grows right on up. Now, I don't want to say anything silly, but even with one space elevator, we can do 5,000 metric tons per year, which is essentially 5 times the total output of all satellites that went to orbit last year. So the capability of space elevators are so awesome that they deserve to be considered really as an important component of movement off planet. So we truly believe that the space elevator is a transportation story of the 21st century. And then humorously, we believe we're going to reach the shoreline of outer space and meet the final frontier. Okay, those are my charts, and I'm open for all kinds of questions. Let me put chat down here so I can see what questions there are. Where's my chat control?
Dr. Swan, can you hear me?
Yeah, I can hear you. That's
good.
It's
at the very bottom. You actually got a good number of questions. You go to the chat box at the very bottom of your screen.
Okay. Chat box.
Yeah, is at the bottom. There should be like a ribbon at the bottom.
No ribbon at the bottom. Ribbon at the top.
Oh, your ribbon at the top for you?
New share, pause share, annotate, remote control, more. Must be under more. Chat. There we go. Nine different ones. Okay. Yeah, we got it here. Okay. So should I start at the top here?
Yeah. Let's go to. Let me bring up my chat box. Maybe we can start with a question from Jack.
Yeah, how to build something like this. Okay, hey, look at that. Nice little coincidence. I hit a bunch of buttons and it came up to the chart showing how to deploy it. What you do is you take a big reel and you go to geosynchronous and you start building it there. You reel down the tether. Now, the secret is you want to stay at that location in geosynchronous, so you have to have an equal mass or commensurate angular momentum trade above geosynchronous as below, so you keep the center of mass right near the geosynchronous location. Then you reel it out some more, and you reel up, and then you end up at the bottom, grabbing it by some ship and grabbing it, pulling it over to your Earth port and tying it down to a reel. And then you have to take the upper end, the deployment satellite, and keep going out a little ways, so you put tension in the tether more than just the support tension. Now you have enough tension in the tether that you can grab the tether and climb. And now that'll be a preliminary tether. You have to then build the initial tether up. Early studies by Brad Edwards show that you have, he came up with the number 298 tether building climbers that would climb the tether and add material. So we've thought about how you do that often. It seems like a reasonable thing. A lot of challenges. I don't want to ever say that we don't have challenges, but just like any good engineer, we ought to be able to beat it. We could do it. It's so worthwhile. We should do it. Okay, and the second part of that question, at what point do you actually affect the rotation? We had a student do the angular momentum calculation for a single space elevator. It was 1 to the 10 to the minus 26, I think, or something like that. Significantly less than the losses to the ocean's movement, or significantly less to the wobble of the moon. Yes, it affects angular momentum of the Earth. No, it's not as significant as you might think. It's really quite insignificant. And we had a student actually calculate that. Let's see, next, how do you prevent damage to the space elevator towers from space debris? Okay, I'm going to give you a quick lesson on that. And then please go download the second report, which was 2020 report, is also a 2010. The way we did it is I got an expert, 20 years tracking spacecraft in the Air Force, a guy named Skip Penny, Lieutenant Colonel Skip Penny. He and I calculated the probability of intersection, or they call it conjunction, of a piece of debris with a tether segment. And we calculated that with computer and all that kind of jazz. NASA gave us the numbers of debris in each altitude region, and then we calculated the velocity of those things compared to a space elevator, which is essentially zero. Not zero, but essentially. So you're humming along, and we calculated the probability of collision. Now, we then did in 2020 the same study with the debris that was actually out there in 2019. So we've done 2010, 2019, and then coincidence of all coincidence, a month before we started the 2010 or 2020 study, NASA came out with the numbers, estimated debris in place in orbit in 2030 after the constellations of communication satellites are put up there. So after OneWeb, after all those other ones are up, the space debris was calculated by NASA, and they gave us density of the numbers with density with reference to altitude. So literally we took NASA numbers, we took an approved NASA approach. By the way, they validated the approach back in 2005 or something like that, 2003, and they actually validated the approach. Then we used the approach, and we have some conclusions. One is, for the big stuff, we got to track it, and then we got to move out of the way. And the way we do it is we do it like a piano wire. We just start a little motion at the bottom, or we start a little motion at the top, and the wave goes all the way up and down the tether, and we can move the tether out of the way. So we can be out of the way of the big stuff. The small stuff is going to hit the tether. Everybody knows that. So you design your tether so it can take small hits, going at 7.9 kilometers per second, but the small pieces would blow through, and you would take those hits, and then you'd have repair tether climbers searching with a little visual searcher, and then you'd patch it along the way. But literally, we take the hits for the small stuff. So we've calculated the impacts for all those small stuff as well as the big stuff and the probability of intersection. The bottom line is space debris is not a showstopper. And if you have any questions, go to our website, and I put that at the beginning of the chat. Download those 2 PDF studies, and then send me a little note if you have any questions. I'll answer them any way you want. I was involved in both those studies. Space debris is not a showstopper.
Hey, Dr. Swan.
Yes.
We have one of the attendees, P.W. Johnson. He has his hand raised. Can I?
Sure.
Okay, yeah. P.W. Johnson, if you're listening, I'm going to try to allow you to hit the loud talk mode. So you should be able to talk now. You have to unmute. Let me see how to unmute.
Okay, while you're doing that, let me answer a quick one.
Okay.
Should it be on the ocean or should it be on land? There's a problem on land in that if you look at the equator, there aren't too many solid countries that are really, for the U.S. and for commercial and could really take over the asset. So you really don't want to put it in a foreign country. So we end up on the equator. Second reason it should go on the ocean is when you're on the equator in the middle of the Pacific, you've got a very Pacific, very calm area. No rogue waves, no lightning strikes in 100 years, et cetera, et cetera, et cetera. The middle of the Pacific is a perfect place to put it. So we really, really like that. We really don't think a land location gives you much advantage. In addition, there's a lot of weather when you're on the land. So let's really put it in the water.
Hey, Dr. Swan, I think we may have skipped a question. It's also from P.W. Johnson, if you can hear us. There's another question, not about the whether it should be water-based or land-based, but what about the debris in low Earth orbit? You could cut the space elevator's cable.
Okay.
To some extent,
I thought he already answered it.
I answered 90% of it. I didn't address the cut. Okay, let's address the cut. We don't believe it'll happen, but we do plan for it. Turns out that there's no real threat other than in low Earth orbit. There's stuff up at MEO and there's stuff at GEO, and you could always have an asteroid, but the probabilities are so small. It'd be like some big bridge falling down. Oh, that happened. So you got to worry about it. So what we're really doing is planning for a cut, if it would occur, which we don't think it will, a cut at say 1,000 kilometers altitude. If you go to 1400, there's a constellation of satellites there. So maybe we could go to 14. But we have plans in place that we'll have to develop. Obviously, we're just early in this, to actually have extra cable at geosynchronous. And if we have a loss of tension, we immediately shoot out tether from geosynchronous. So then we let the tether fall and you grab it and you have it back. In addition, we have an ancillary idea, which I really think is the right answer, and I think will be implemented when we build the tether, which is at 2,000 kilometers, we'll stop having a single tether and we'll put 4 tethers down. So if any one is cut, you still have the other 3 to hold the tether, the space elevator together, and then you move, you know, the best of 3 over to the Earth port and you start all over again. So we really have addressed the space debris issue. It's all in those 2 study reports. Yes. Go ahead.
P.W. Johnson, you can talk if you, can you hear us? I
guess we lost him.
Okay. Well, if you want to chime in at any moment, that's fine. Did you want to move on to the next question?
Yeah, the next question is what happens to the climbers? Oh, we love climbers. It turns out that what we need is a mass at the apex anchor to provide the outward force to keep the tether nice and stiff. The problem is when we deploy our first deployment satellite, goes out all the way there, reeling out everything, we don't have enough mass up there. So we plan on most of our original space tether climbers would just deposit their payload wherever it's supposed to go, let's say geosynchronous, then it would continue out to the apex anchor to become extra weight. In addition, at the geosynchronous, you'd probably take off all the valuable parts like solar cells and use them someplace else, because going outward is a downhill activity. You're away from geosynchronous. There's more force outward than gravity attraction to the Earth. So all you need is brakes going out. You don't need a motor. So we could take the motors and all that kind of stuff out of the tether climber and use them to build something else at geosynchronous. The very valuable things would be things like batteries, solar arrays, computers, comm links, and all that kind of stuff. So we're going to kind of like, what do they call it when you're a cannibal? Cannibalize our tethered climbers and then just send the mass out to the other end. Okay. Let's see, what happens when it breaks? Okay, same thing. Cost per kilogram of graphene. Well, right now, the cost per kilogram of graphene is about $1 billion. So I think we're kind of like out of touch there. But if you remember the chart I showed, which was the strengths of graphene, it's going to be a miracle material. Let me give you one example. It turns out graphene will pass water molecules and very little other stuff. It's a great purifier. So just as a tool to purify lousy water around the world, graphene is going to be produced in huge quantities. So the price of graphene is going to come down big time. And once you have this strong a material, this lightweight of a material, it'll be used for bridges, it'll be used for roads, it'll be used for all kinds of things. One of the problems, I find all kinds of little facts along the way. One of the problems today is we don't have a material that's strong enough to carry a elevator from the basement to the top of the largest buildings. You have to go up so far and then go to another elevator. You can't go all the way. They just don't have a capability today to do that with cables. So this material would now open up cable elevators all the way to the top. So it's going to be a commercial success, and then we're going to leverage that. Okay, how does the radiation magneto tail impact the space harbor? Oh, okay, let's broaden our term. the space harbor, the galactic harbor on the ocean surface wouldn't be affected. But once you leave the atmosphere, and get into the rest of the sphere around the Earth, we are going to be dealing with the magnetic tail of the Earth and the magnetic tail of the sun. Now, it turns out I have been asking that question, that exact question, for about 20 years now, and nobody can give me a good answer. But now there's good hope. Turns out a good friend of mine who has got a PhD, and his expertise is electromagnetic fields above the atmosphere. He's been working for Lawrence Livermore Labs and the accelerator up there. What's the name of that? Linear accelerator up there. He's now retired from there, and he's working out of New Mexico, and he's supporting as the vice president of ISEC. And I have the question now directed to him, and he's going to start putting some serious time to look at electromagnetic coupling with a space elevator. Good, bad, use it, throw it away, whatever. So we're going to actually address that particular question more forcefully in the next 2 or 3 years. I think it's an important question. Oh, space elevators on Mars and moons. The answer is great, good idea, let's do it. I published a paper at the International International Astronautical Federation Congress, I think 5 years ago. The title was Earth, Moon, or Mars, First Space Elevator, with a big question mark. The answer is they should go on all of them. But the bottom line is, if we don't get out of our stinking gravity well, we don't need no stinking space elevators on the moon or Mars. We're not going to have enough traffic to use them. So we have to beat big gravity. We must do the space elevator on the Earth first. And then, now in our book we're going to publish in a month, we have a vision chapter at the end. And in that vision chapter, we say that the space elevator should toss from one apex anchor to another apex anchor. And the other apex anchor ought to be on the moon elevator, on the Mars elevator, or maybe even on an asteroid elevator. But we should go space elevator, apex anchor to apex anchor, so that we can use rockets for what they're really for, which is moving around and making sure we're in the right place and going to low Earth orbit and going to places that aren't compatible with space elevators. But when we can use space elevators, it's so smart to use them. Let's do it. So the answer is Earth space elevator first, and then the moon and Mars right after that. By the way, we could toss all the material there from the space elevator, so we don't have to build it there. Are there sweet spots where you put these tether in the Earth? Yes. There was a beautiful master's thesis done by a young man who was from Norway that studied in Japan, who was traveling the Pacific, I think just to travel the Pacific. But anyway, he came up with the answer, Christmas Island at Kiribati or something like that. And it's an excellent position. It's straight south of Honolulu. It's a really nice place. The bottom line is we need to be on the equator, and we need to be in an area that doesn't have rogue waves and big weather and all that kind of stuff. And there's some nice locations, 2,000 kilometers to the west of the Galapagos that would just be about right. But you can also be in the middle of the Atlantic or the middle of the Indian Ocean and do the same thing. So who's going to fund it first? Who knows? Where it's going to go? Who knows? But it should be exciting in the overall planning. Let's see, 4 tethers should prevent the loss of the tether in case of a 9/11 aircraft attack. Yeah, we got terrorism. Just like anything you do, bridges, water, whatever you're doing in today's society, you got to have terrorist protection. We figure that we'll have submarines going underwater to protect us from there. We'll have helicopters in vertical takeoff that can lead from our little platforms and protect us there. Yes, if somebody wanted to destroy us, they could destroy us just like any bridge or anything else. But we do a modest amount of defense. And of course, just like any airport, you got to make sure you check everything going on the airplane. So we'd be checking everything going on the tethered climber. climbers be powered? That's a big question. There aren't no real answers there, but I'll tell you what my answer is. My answer is we've got really, really good solar power. So what we do, by the way, there's been some great breakthroughs for solar power up to like 40%. We're flying 28% right now, efficient solar powers. So we're going to get to 40 and 45% pretty easily, I think. So we have very, very efficient solar power systems. Now the question is, when do you deploy the solar power? Well, you got to get it above the atmosphere. So we've had 2 or 3 reports that have talked about the tethered climber. And when we talk about the tethered climber in the atmosphere, multiple approaches to that. One is which is a high stage 1. We have a design by a very smart guy who said he can put a platform at 50 to 60 kilometers that can hold up 400 metric tons. So what we do is we take our payloads up there, load them to the tethered climber up there, and then let the tethered climber already have all of its solar cells deployed. When the sun hits us at daybreak up there, they start climbing. So it would be stage 1, go the first 50 miles, and we just use a pulley to do that. That'd be no sweat. And then we would attach it to the tethered climber and go from there. There are other approaches. It depends on who you talk to and whatever. But the bottom line is we've talked about that many, many times. The original study by Brad Edwards always talked about laser power. But when we finally tied them down, they're talking about a gigawatt of power for each tethered climber on the surface of the ocean. So if you have seven tethered climbers, that's 7 gigawatts power in a local area. I don't really like that. And doing powerful look up, how many optical systems up there, Earth sensors on every satellite. It's a bad juju. I don't like that. Anyway, can you bring cargo back using the space elevator? Right? Yes, of course. Whoops. Who said that? Slap my hand. My feeling is that most of the value for space elevators is up. And so we put 2 tethers together, call it a Galactic Harbour, and you go up with 100% on one of them, and the other one you go up whenever you can, and if you have to come back down, you come back down. But here's where my engineering hat gets really, really tight. Going down into the gravity well is a bummer. And when you're in space, you've got to have brakes because there's no atmospheric slowdown. So now you've got heat. You got to get rid of the heat. So you got to have big radiators. Everything has gotten out of hand real fast. So coming down on the space elevator in the region of big gravity, moving around above MEO, middle Earth orbit, and all the way out to GEO and beyond, nobody cares. You can go up and down, no sweat. But when you're in the gravity well, you're really stuck. So what do we do best? We really like capsules. So what we do is we take a capsule up on our space elevator to, let's say, 2,000 kilometers up, where we have our little combined region with the 4 space elevator segments, and we bring tether climbers down to 2,000 kilometers or down to 4,000. You climb into a capsule, and then you enter the atmosphere with the capsule. But trying to beat big gravity coming down is a big problem. So my answer is, let's go up for a while, and then if you need to come back, let's ship a capsule up and ride the capsule down. We know how to do that, and it works well. And it gets rid of the gravity real easily by heat. You can't do that in a space elevator. That radiator problem is a real biggie. Okay, power, climbers power, come back, bring cargo back. Yeah, we can bring cargo back, but it's a bummer. Will tethers have electrodynamic static charge buildup along their height? You bet your sweet bippy. But I don't know how much, and I've asked that question for 20 years, and we need a good electromagnetic person who understands the electromagnetic fields above the atmosphere to look at that real hard. Now, the reason we really haven't pinned that down is we really didn't understand the electrical characteristics of our potential tether material. Now that we know it's going to be either single crystal graphene, which is a perfect conductor, or hexagonal boron nitride. By the way, that's coming along as the front runner now. Boron nitride is basically the same strength and same buildup and everything, but boron nitride is a perfect insulator. So one's an insulator, one's a conductor. I don't know which we need, so we'd have to work on that. But there will be electrostatic charges. We will have to worry about that on our tethered climbers, in our payloads, in all that kind of stuff. It's the standard issues in space. When you're up there, we understand that pretty well. Okay. I hope that the Zooms are going to be available someplace, and David is working on that. So we'll
this is David here. Since this is our first webinar, I'm still kind of learning the details of Zoom. From my understanding, we are recording it, so we will be posting. The goal is to post this on YouTube. I don't know how it's going to work out, or if it's going to be like, my concern is it might just show my screen and show all my like chat box I'm looking at. I'm hopefully that's not what's going to happen. It should just be recording what the speaker, what Dr. Swan is actually showing when he shares a slide. I think that's what it's going to show. So we're going to get through this, and I'm going to see how it works. But yeah, the goal is to record this and future Zoominars and put it on our YouTube channel. That way we have like a library that will keep all the stuff in. And once we go back to the downtown library, the goal is to record stuff with like a camcorder or some like camera, and then also do it and also post them to our YouTube channel. So we're going to be working on that, but that's something that we definitely want to do, is recording stuff.
That's great. I'm looking forward to that also. One of the questions that is, can you recommend sci-fi and other books, etc., for utilizing space elevators? It turns out a lot of authors have used the space elevator in their materials. Heinlein had it in a book called Friday, but the classic one is Arthur C. Clarke's Fountain of Paradise, and it's a good read. If you want to learn more about the space elevator, our ISIC has 10 study reports, and we have a 200-page history book on space elevators going all the way back to 1895, talking about space elevators. So we've got a history of space elevators. We've got the engineering of it. And then if you go on the website and search for, fiction and space elevators, there's got to be 100 books out there. And there are some good ones and some that are bad. But I still think Arthur C. Clarke's book is probably the premier book on space elevators. Let's see what it is.
We got a new question from Steve Hall. I don't think, let me see, that the latest question is somewhere there in the comments. Yeah,
there it is.
Next question to you is the Steve Hall one, number 5.
Yeah. Do tether material properties change, long-term degrade? Have no flipping idea. But let's put it this way. We have a lot of good space people, and they have a lot of experience in a lot of stuff, and they'll tell me what the story is. But I do know that the Japanese have flown tether material in space to test it out for exactly those things you're talking about. Charge, conductivity, resistance, atomic oxygen eating away the surface, all that kind of stuff. We have some really, really good experts in space material analysis in the Japanese contingent of space elevators. By the way, the Japanese are very, very, very good at space elevators, and they've got an effort inside their government to build space elevators. The Chinese have said they're going to have a space elevator by 2045. So there's some activities out there that are exciting. But literally, the materials will change. We have to plan for it. We have to implement either fixes or modifications or something for the materials because we do it. Now, the good news is we've got a lot of experience in space. The bad news is we really don't have much experience beyond the magnetosphere of the Earth. And when the Earth is pointed, or when the space elevator is pointed toward the sun, we literally break out of the Earth's magnetic fields and go into the solar magnetic fields. So I'm not sure how having a wire going from one set of magnetic fields to the other magnetic fields is going to work. We might have a big short, we might have a big installation. I don't know what's going to happen. As I said earlier, we've got a really smart person on the board that has expertise in this area, and I'm hoping we do a big study on that sometime in the near future. So it should be a good set of questions. How does the space environment affect the materials, and how does the electromagnetic environment affect the tether?
Hey, Dr. Swan, kind of as a follow-up to Steve Hall's question about the material properties changing, my thinking is, for me personally, is that the cold vacuum of space, oxidation won't be a major issue, I think. But when you talk about the low temperatures, everything's going to become brittle over time. I'm wondering how the brittleness, due to the low temperature, all the materials basically freezing, I'm thinking that's going to be a major concern. And like you said, there could be major temperature fluctuations as you expose it to, like, say, if you get, for example, sunlight. I could imagine there are going to be very violent freeze-thaw cycles where you're going from low cold temperatures and brittleness to these a bunch of thermal shock when you expose it to, for example, sunlight.
Yes,
and
definitely. I agree with you.
Temperature swings are going to be a huge challenge, and I'm really wondering how, can you make the material resistant to it, or you're going to have to sit there and like go up there and replace parts?
We have a lot of really good space scientists / engineers that are very, very cognizant of all those issues, and I agree with you completely. The good news is there are a lot of people in NASA and all their contractors looking at that particular issue right now, because we're going to put people on the surface of the moon in 2024, plus or minus. And to do that, we have to take care of temperature swings of 350 C instantaneously for the materials we're using for all that. So all we're doing is joining along with all the other people who are proceeding into that hostile environment. And it is a hostile environment, no doubts about that.
I mean, it's a harsh mistress.
Yeah, and we got to deal with it. But the good news is we've got a lot of experience, and we got a lot of smart people, and we give them the right problem, and they'll help us with what to do about it. One of the first things we got to do is take single crystal graphene and fly it in space in a vacuum and experience these activities like atomic oxygen eating away the surface, temperature swings, vacuum, all those things. We definitely have to have experiments in space to understand the effects of those things on our material. No doubt about it.
I don't think we missed any questions or comments. Does anyone else have any other comments you want to put into the chat box or Q&A? Let me see just the Q&A real fast. Okay, you already answered the question in Q&A. Where can we get the brief? I guess we could. I guess you could send that to me, and then I can try to post it to our.
Yeah, I'll give you a PDF later today or tomorrow.
Yeah, you know what we could do? One thing we could try, we've never done this before, but one thing we could try to do, if it's a PDF, we can probably put a link to it to our on our website, and then we can just be able, people should be able to just download it from there, because I know we can download our flyers from as a PDF. So I think putting in the brief on our website would actually work. Yeah. So yeah. Jared, I will send you a status update when that is ready, and I'm going to put my email address again for anyone else who wants to find out about the brief or a question for Dr. Swan. This is my email address, steve_delft@yahoo.com. So feel free to send me any question. I'll probably just So just feel free to contact me there, and you can, once I get the brief is ready to go, you can contact me about that. I'll probably put that inside the next newsletter. We got some more questions coming in.
Oh, I was just answering the space graphene experiments lend themselves to inexpensive CubeSats. Yes, that would be awesome. Can you hang comm systems on the space elevators and alternative something like Starlink? Yes. The use of space elevators is just awesome. You could do all kinds of things. The one counter to it is you really can't put a lot of mass on the tether because it weighs down the whole thing. And the danger is too much mass, tether break. So we have all kinds of numbers in there. You could do that, but I truly believe we're going to end up with scientific experiments. So one space elevator is going to go up there, and we're going to put scientific instruments every kilometer, 100,000 boxes. Each box, of course, would be different for the different regions. But we do not have information, scientific information, at so many locations in space, because all we do is go through it. We have a whole bunch of information at geosynchronous. We got a whole bunch of information at low Earth orbit. But we have almost no information beyond geosynchronous. And that's the electromagnetic region for the Earth. We need to understand that for science on the Earth. So we need scientific packages on a space elevator, but we'll probably have to dedicate a whole space elevator so we can spread the mass around and not destroy the space elevator. But those are all ideas and concepts that we can develop over time. Where will the maintenance personnel live? I have no idea. But the answer is that in the long run, we'll have people assembling satellites at GEO. We'll have people assembling starships that are going to another solar system at the apex angle. I did a paper on let's go to a star leaving from a space elevator. And what you can do is assemble the Starship Enterprise at the end of the tether. Then when you release it, it has escape velocity from the solar system. You've got to have rockets on it anyway. So then you have rockets add energy, you go by, do gravity assist. And when you leave our solar system, you can really be hauling and get to this next star system in a reasonable time. Reasonable being questionable. But, you know, I designed that for a paper at the 100-year Starship Convention, I don't know, 5 years ago, something like that. So yes, we'll have people living all along that in the long run.
That's interesting. Do you have any more questions for anyone or for Dr. Swan?
Okay, well, I really appreciate this because what you guys did is take me out of my comfort zone. I had to go re-look at all that L5 stuff and Gerald K. O'Neill stuff and try to understand what it would take to really support an L5. And when I was growing up a young pup, you know, like 28 or something like that, when I was a young pup like that, I really, truly believed that we would be well beyond the moon when the century turned. And we were really looking for, you know, an L5 colony, looking for being on Mars by the turn of the century. I mean, we were looking for all that kind of stuff. And so the whole idea of having a capability to deliver 200,000 metric tons per year in support of movement off planet, I mean, that is awesome. We really, really enjoy working in that that field, that projection of the future. It's fun. So I had to really stretch my mind and push the envelope a little to figure out how we can apply it to L5 versus going to Mars, which was a research project that was accomplished.
Oh, Dr. Swan, we have Tim Weaver is on the microphone or is on the audio platform.
Good.
But Tim?
Yeah. I was wondering how you thought about using the space elevator first for the moon. Setting up on the moon first.
Well, I answered that a little while ago, but the bottom line is I want a space elevator on the moon and Mars and every place else. The bottom line is you're going to have no users. There's no users. There's no demand. If we use rockets to get up there, there's no demand. Think about the numbers of people we're going to get up there, and the first few flights and how long it's going to take to get a colony on the moon. If we can use space elevators, we open up the whole environment. Then we need a space elevator on the moon, and we need a space elevator on Mars. There's no doubt about it. We need space elevators at all those places. But we have to beat the gravity well first. Bottom line. Until we beat the gravity well, we're going to be using the stinking rocket equation, and you guys can do the math. 4% to low Earth orbit, 2% to translunar insertion. I mean, I love rockets. I mean, I'm an Apollo guy. I love all that kind of stuff. But if we can do better, shouldn't we do better? Let's see, what a stratosphere. Other use video. Okay, what the question from Bill is that would a stratospheric deployment of the tether test? Yes, we could do a testing there. I like that answer. We'll probably do a testing in the atmosphere to work on strength and climber capabilities, all that kind of stuff. But I have in my schedule a prototype Pathfinder experiment. Now here's the parameters that I would like built. And I think we can do it within 5 years. 1,000-kilometer tether deployed up to a center of 2,500 kilometers altitude. So you're in the radiation belts. Your electronics have to be able to deal with that. So 2,500 kilometer altitude, 1,000 kilometer long, so it's 500 down, 500 above. And you have to deploy the tether using a deployment satellite. And then we're going to have a mass at the bottom we call the Earth port. Of course, it's going to be at the bottom of the tether going around to Earth, but we'll call it the Earth port. And then we'll have tether climbers going up and down, and we'll have an apex anchor at the other side, and we'll have release from the apex anchor to show that we can actually toss things from the space elevator. So literally, we can test out single crystal graphene in space. We can look at coefficient of friction. We can look at the sun temperature on off, the vacuum effects, all that. And we can test out tether climbers. And if you do 1,000 kilometers, people get serious about that. That's a serious experiment. So I really believe we need a prototype to fly in space that's 1,000 kilometers long, based at a circular orbit of 2,500 kilometers circular as a center of mass. Now, I think we can do that within 5 years. This is where we have to transition from, I keep using the term academic, although a lot of us aren't academics, but from an academic look at space elevators to a developmental look at space elevators where somebody's actually funding the development of the tether climber, the tether, the Earth port, the apex anchor, and all the different aspects of the whole process. So we need funding is where we're at right now. And I'd love to do a prototype Pathfinder experiment in space. But yes, we have to do something first on the Earth. All spacecraft are tested in some way on the Earth. We put them in a vacuum, we put them someplace, we test them. We need to test the tether climber, we need to test all kinds of stuff. So yes.
Yeah, I have another question.
Sure.
Okay. Let's see. All right. What about an orbital ring? I wonder if you're familiar with that concept.
Oh yeah, yeah. We have an orbital ring guy come talk to us every 2 or 3 years in our conference in Seattle. The answer of an orbital ring is fantastic. Wait a minute. How much mass is that at GEO? How do you get it there? You're going to use rockets? I mean, be serious. I know. I'm talking to Rocket City, okay? I know you guys are down there in Huntsville, but let's be serious. Rockets are spectacular. They've gotten us to where we are. I love rockets. I grew up with rockets. I'm an Apollo guy, okay? But let's be a little bigger than that. Think about alternatives. And space elevators the best alternative at this point. Now, once you get the capability to break out of the gravity well, then orbital rings are fantastic. And they can really be developed because you can take mass up to the altitude you need it to go up to. So I love orbital rings. Just don't do them first because, well, you can't. But anyway, other than that.
Let's see, Bill did ask another question.
All right, thank you.
Sure, Tim. I know, how do you protect it from space debris impact? That was kind of a pretty popular question tonight about the space debris issues.
Got 2 reports on that. Download them and look at them.
All right. So, Bill, if you want to, you can always contact me or Dr. Swan. We can probably send you those reports if you want to go through the gory detail. That was actually a pretty popular question tonight about how do you protect it from like micrometeorites and other debris, what have you. I think that's definitely going to be a huge question or a huge concern down the road.
I'm putting the website on there. Go to website, go to studies, download PDF for free.
Yeah. So, Bill, there's a go to that link there, and we should be able to find, for those who want to go through the details of it, about the whole space impact problem. There's some number of studies already done on this.
Remember, they were done by a space debris expert who spent 20 years tracking stuff in space in the Air Force. And if you want to go to that website and sign up for the newsletter, and you can keep up with what's going on then.
Okay, so almost about 8:30 right now. So I guess this is probably maybe a good time to wrap it up. I don't think there's any more questions coming in, but if you have any more questions, you could, Dr. Swan, are we allowed to contact you?
Oh yeah, no, I gave everybody the thing. I'll put it out there again. It's pretty straightforward.
And also, there was another comment about you coming back down the road to give us any status updates.
Oh, I love this stuff. Yeah, David, all you got to do is let me know, give me some advance so I can put some charts together. You know, if you want me on a panel or something to sit in, I'd love to do that stuff. As I said to my neighbor recently, my next appointment is Wednesday. So, you know, we're kind of like not being too consumed here.
Excellent. Yeah, because probably with the, now that we're going to with the quarantine and trying to test out webinars, I might be wanting to explore, maybe we could even try to do, even when we go back to the downtown library, we probably consider doing deep dive webinars and just, you know, have people who aren't local to Huntsville come in and to Zoom and give talks that way and have other panelists that way do all the deep dives. And it revisit this topic.
Fine. Yeah, I'm also available for talking about my other company, which is called Planetary Services. We are doing prospecting of minerals on the moon from orbit by sending penetrators in and retrieving the sample. And so it's a really neat concept, but we're doing it commercially as a small company, and so we're charging ahead. The idea is to pick up a sample in the permanently shadowed region and give XY location to anybody who wants to chase down where the water is. So we take a bunch of samples, tell everybody what the distribution of minerals are in the permanently shadowed regions so that they can know where to go when they want to get the water ice. So it's a pretty neat little concept, fun stuff.
Like a survey, right? Kind of map out the whole surface.
Yeah, it's a prospecting. The term in mining is prospecting, and that's what we'd be doing.
Okay, neat. Yeah. Okay. Well, with that, then I think this will be a good time. This is now 8:30, pretty much right. It's about 8:30 now. Let's see here. Yeah, it's 8:31 exactly. I think this is probably about 90 minutes. It's normally the time that we do end the talk anyway. So with that, I'm going to wish everyone a good evening and thank you again for joining tonight's talk. And we'll be having, again, another talk will be on July 9th here at upon our Zoominar. You go to the webpage, or again, feel free to contact me, and I'll put down my email address again as we kind of try out this whole webinar feature. putting down my email address. So feel free to contact me and or go to the webpage, and we'll be sending out more details about the July talk. And with that, I'm going to end tonight's webinar. And again, thank you for attending, and also thank you, Dr. Swan, for your talk tonight.
Hey, I really enjoyed it.